All right, so we were sitting right here and we noticed that this was logarithmic scale. And you can tell, again, I said it in the last video, but I'll say it again, because it's not going up by the same amount every time. Linear goes up, right? That's because linear has slope, right? If you remember slope from algebra class. So you go 10,000, 20,000, 30,000, so on. This gets multiplied. 1,000 times 2 makes 2,000. 2,000 times 2 makes 4,000, and so on. Right. And I just wanted to show you on Gapminder, if you go to gapminder.org and you click on Gapminder World, the graph that you get is the same graph that you're looking at here. The only difference is that I made it so all the dots were not colored and I made it so all the sizes were down. I'm not going to do it right here. This is actually a more useful graph. Oh, and it was back in 2009, so you can move the little arrow thing down here and pick a different year. But this one was 2009. There it is. Oops. Go back. Having issues. There we go. Got it. Okay, so when we look at this graph, right, we can see that the horizontal axis is now, oops, logarithmic. It's multiplied by 2 instead of adding 10,000 to get the tick marks. Oopsie. Hold on one second. There we go. Now I got to fit in there. All right, so we're multiplied by 2 to get the tick marks or the vertical axis lines rather than just adding 10,000, which is what this one is. Okay. You can also see it in the bottom right corner. Log in the bottom corner, which tells us this was logarithmic scale. All right. Now, what in the heck is logarithmic scale? Well, you were seeing it a little bit there. Linear scale, which is what you're far more used to, goes up by the same amount every time. So 1, 2, 3, 4, 5, or in this case, 10,000, 20,000, 30,000, 40,000, so on. All right, logarithmic scale doesn't do that. It multiplies like I was showing before. So in this case, 1,000 times 2 is 2,000. 2,000 times 2 is 4,000. 4,000 times 2 would be 8,000, which would be in there somewhere, right? 8,000 times 2 is 16,000, and so on. Okay. And they don't have to keep the same numbers showing. They switch to more practical numbers like 1, 2, and 4 in here, or 10, 20, 40. All right, so when do we want to use linear scale and logarithmic scale? A good rule of thumb is to use the scale that best shows off your data. So presentation of data on a logarithmic scale can be helpful when the data covers a large range of values. For example, like incomes in a country. You can have some really poor countries that really are 400. Look, check that out. You have some countries that have $400 per year GDP. And then you have countries that are, in the 50,000, 60,000, 70,000, and so on. Okay? If that's the case, if you're trying to cover that much distance, it's better to use logarithmic because otherwise, look at all the countries. If you look linear, everything gets crammed in over there. Whereas logarithmic spreads it all out. And that's more fair, actually, in this case because income has such a wide disparity, right? Wide range, if you will. All right, so the use of logarithms of the values rather than the actual values reduces a wide range, really wide like income, to a more manageable size. In other words, we use logarithmic scales not only for exponential data, but for data that's really tightly packed in. We're only going to be looking at logarithmic scales. We're not going to compute them at all. Log scales are often used in science. pH is a log scale, decibels, like as in stereo decibels, Richter as in earthquake, that's all logarithmic. All right, so here are two graphs. They are for the exact same data set. See that? So the U.S. spends most money on healthcare in the world. Circle the U.S. in both graphs. All right, let me do that. I'll be right back. There we are. So we are the most expensive. So we're number one in something. We are the most expensive healthcare. So we are the farthest to the right. So that's us right there, and that's us right there. That's the U.S.